In this video, we're going to introduce Kirchhoff's current law to you. Let's start with a couple of resistors. They're connected at one node, so that means they're connected in series. There's our one node. Let's just give them names, R1, R2. And let's suppose that some current flows in and another current flows out. Now, what you'll notice about this node is that there's no device at this node that can store charge, or generate charge for that matter. That means that every bit of charge that goes in has to go out. So we'll say that I1 has to be equal to I2. This is a consequence of the conservation of charge, right? Charge is neither created nor destroyed, but there's no way to store or generate charge at that node. So this is an important relationship, and we'll generalize it. There are several ways to generalize this, and the first way we'll say it is in terms of currents entering. So all currents entering are zero. So let's write that out. We have to be careful about what we mean by currents entering. We actually have to deal with all currents entering the node. And so in our example, there are actually two currents entering the node. I1 is the first and most obvious current entering the node, but there's another current. It's actually not I2, but negative I2, because I2 is leaving, so negative I2 is entering. And that satisfies this equation that we wrote down. We'll call this form A of Kirchhoff's current law. Okay, so this relationship right here gets us the I1 equals I2 from above. And so that's validation and verification of what we know from conservation of charge. There's another form we can think about. Let's try form B. These are arbitrary names, by the way. I just made them up, form A, form B. But now let's sum all currents leaving. They have to be zero. So the currents leaving the node, well, here I2 is leaving and I1 is entering, so we actually have a negative I1 that's leaving, and that has to be zero. And again, this gets us the exact same relationship as before, I1 equals I2. There's another form where we say all the currents entering, let's put in here, I guess, has to be equal to all the currents going out. In the simple example given above, you have I1 is going in and I2 is going out. And that's consistent with all the other relationships above. Notice that A and B are only different by a sign, so they're completely mathematically equivalent. All of these statements, form A, form B, form C, mathematically equivalent. Let's make it a little bit more complex and a little simpler at the same time. We're going to ignore the elements. So let's say we have 3 branches coming in, and we've arbitrarily defined 3 currents. If we wanted to use form A, we're going to think about all currents entering. So we would put I1 is entering, negative I2 is entering, and negative I3 is entering. Those have to equal 0. Form B, mathematically equivalent. All currents leaving, well, negative I1 is leaving, I2 is leaving, and I3 is leaving. All those have to sum to 0. Form C, I1 equal to I2 and I3 summed together. You see here everything's mathematically equivalent, mathematically consistent. The only thing you have to worry about is you have to pick a form and you have to be consistent about the signs and directions. Let's make a related example. Let's say we know 3 amps comes in this way, 5 amps comes in this way, and then we want to know what current is going in here like this. What is Ix? So in this case, we would write a form. We pick a form. I'll pick form A, for example, all the currents entering. So 3 amps entering and a 5 amp current entering and an Ix entering. That's everything. They have to sum to 0. Ix is negative 8 amps. That tells us that positive 8 amps is flowing this way. And you can kind of intuit that now. When you think about this node, well, if I have 3 amps and 5 amps going in, well, then 8 amps has to leave by that third branch. But Ix is defined opposite to the current that's leaving, so it's actually negative 8 amps entering or 8 amps leaving. Now let's consider a circuit example where we can learn from Kirchhoff's current law. Now we can ask ourselves, how much current does the voltage source supply? Specifically, Ix is equal to what now? That's what we're asking. We know that we have 3 milliamps going this way. We would like to know what the current going in this way is. Let's call it Iy, because then we could write from form A that Ix plus Iy plus 3 milliamps equals 0. That would be KCL at that top node. Now we have to figure out what Iy is so that we can unlock what Ix is. We can do that if we pay attention to what the nodes are here. I see one node and a second node. Let's call them A and B. This battery leads us to know that VAB is 10 volts, right? A is higher than B by 10 volts. Now, if we want to figure out Iy, well, we need the voltage drop in the direction of that current. So Iy is going like this, right? That's the current through that resistor. Well, that is VBA, right? Because VBA is defined in that direction, with the plus side being here and the minus side there. And that is consistent with the passive reference convention. It's VBA, not VAB. So VBA and the 5 kilo ohm resistor are going to be what gets us Iy. Well, what's VBA? Well, we know VBA has to be negative 10 because VAB is 10. So Iy then is negative 2 milliamps. So we can write Ix is negative 3 milliamps minus Iy. And filling in here negative 2 milliamps for Iy, well then we have negative 3 milliamps plus 2 milliamps is negative 1 milliamp. So a couple ways to think about that. So Ix is here. It's negative 1 milliamp. It's also equal to 1 milliamp traveling in the opposite direction. So let's summarize that and just make sure this makes sense. Here is our node, just simplifying it. Here's our Iy. We know this is 3 milliamps, and we've come up with that Ix equals negative 1 milliamp. That is equivalent to 1 milliamp going down rather than up. And Iy, we said, is negative 2 milliamp, but that's equivalent to 2 milliamp going the other direction. We should look at this and see that it in fact makes sense. Because you see we have 3 milliamps entering the node in this direction. We have 2 milliamps leaving. Well, where did the other milliamp go if we're going to conserve charge? Well, here it is. It's 1 milliamp leaving in that direction. So this could be written in the form of A, B, or C as above. There is a simple example of how Kirchhoff's current law can help us discover unknown currents. So here I used a Kirchhoff's current law equation. I then used Ohm's law to identify one component of that equation, and that allowed us to unravel the last part. And finally, we checked our answer to see that it makes sense. I hope that was a helpful introduction to Kirchhoff's current law. Please like the channel, subscribe, and share it with others. Have a great day.